This is the fourth video lecture about lexical analysis, and we're going to talk about how to actually implement regular expressions. How can we actually match strings using regular expressions so that we can use it for our lexical analysis tool. So far, we've seen that we can write down a pattern or a particular token in our compiler as a regular expression in order to describe all of the lexemes for that token. So if I wanted to describe a token identifier in some programming language, I would write down the definition of T identifier using some regular expression. Now what I want to do is take this regular expression and actually match some lexemes, or in the case of an identifier, I want to match the identifiers in this programming language. The problem that we need to solve is given a pattern that's described as this regular expression R, and we're given some input string S, so that's like a candidate. You want to check, is this an identifier or not, for example? Then we need to say if S belongs to the language described by this regular expression R, then we should return true, so we can identify it correctly. But at the same time, if this string doesn't belong to the language of R, then we should return false. If I see an input 12, and I have a regular expression that matches identifiers, like here, then I know that if I match this regular expression for this number, it shouldn't match. But if I have like x12, something like that, then it should match. So that's the problem we're trying to solve, is we've defined it as a regular expression, but now we want to actually get an algorithm to do the matching for us. This decision procedure is called a recognition algorithm. So the way we do this is by taking a regular expression and converting it or compiling it into a data structure, which we'll call a finite state automata. And a finite state automata can be either deterministic, in which case we call it a DFA, or non-deterministic, and we call it an NFA. And we'll see in more detail the differences between them. But to start off with, let's just define the notion of finite state automata first, and then we'll distinguish them into DFA versus NFA. They each have their own recognition algorithm, but they're both equivalent in one sense, in that they both solve the same recognition problem. So they're both equivalent. If I have a regular expression R, then I can construct a DFA or an NFA from it. I can use either the DFA or the NFA to solve the recognition problem. So I can, use either of them, but we'll see the pros and cons of each as we dig into deeper what these finite state automata are. We will use a common way of representing all finite state automata. So let's first define what that would look like. So we start off with a finite set of input symbols, just like we defined it for regular languages and for regular expressions. So it's basically the same idea. We start with some base case of the symbols, and then we'll build representation based on the alphabet. We're going to have a finite set of states S, and this set of states is going to represent sort of where we are in the regular expression, so which part of the regular expression we are currently recognizing. And these set of states, there are three types. There's sort of general states that are sort of somewhere in the middle of the finite state automata. There's a special start state, which we'll call Q0. And then there are 0 or more final states or accepting states. So when you reach a state that's in this set F, that means we're done, like we've recognized a string. And that means we can accept the input string. And if we don't reach a final state, that means that we should reject the string. That means the string is not in the language of the regular expression. We're going to use a graphical notation to draw these finite state automata. And so these states S are going to be represented by some node in a graph, which is drawn as shown there. And the start state is shown just like a normal state, but with a bold sort of boundary so that we can recognize it's a start state. Some people often show an arrow coming in to the start state to graphically sort of emphasize that that's where you start. And there's only one start state, just to keep things simple. And then there are 0 or more accept states in this state F, and they are drawn with the double boundary circled so that these nodes are distinguished as the final state. We can go from one state to another. So we have an input state and an output state. And a function delta is defined that takes us from one state S to another state S if we see some input. So it matches some input symbol and then goes from one state to the other. So this transition function of this type that is shown there is telling us how we can go from one state to the other. So we start from the start state and we start going from one state to the other until we reach a final state if the string is a valid input for this finite state machine. So a transition function is shown by using an edge between the nodes in the graph. So here's an example, which is this function. There's a transition function, takes two inputs. So the first input is state 1 on an input symbol A, will end up going to state 2. So graphically, we would show this as state 1, right? We start from the state 1. And on an input symbol A, we take this edge, which is a directed edge, and go to another node in this graph 2. So what we've done is taken one symbol from the input and sort of progressed in this finite state machine from one state to another state. So let's look at some examples. Here's a very simple example of a finite state machine that accepts only the string 1. So if you think about the language accepted by this finite state machine, it's a set containing exactly one element, which is the string 1. And we start on the start state over here, and we go, if we see an input 1, we end up in this state B, and that B, as you can see from the visual cue of the doubled circle, is the final state. So if I start with state A and I'm taking some input, then I would scan past that input symbol 1 and end up in state B. If I was at a final state when I'm done with the input string, so here there's no other symbols after this sort of input sort of scan head, then I would say that it has accepted. If my state doesn't have a transition on any input symbol, so here starting at A, the start state, it doesn't go anywhere on a 0, so we can reject this string because this finite state automata doesn't accept this as a valid string. And I could accept a 1 and end up in state B as before, but I still have another symbol 0 here. You can see that from B on an input 0, I can't go anywhere, so I would reject this string. So that's how a finite state machine can be used to accept or reject input strings. And the idea is it should accept all of this. The strings that it accepts is the language of this finite state machine, and the strings that it rejects, that doesn't accept, are not in that language. So the set of strings that it accepts is defined by this path from the start state all the way to a final accepting state. Another example here is a finite state automata accepting any number of zeros followed by a single 0. So if I was to write this down as a regular expression, I would write this down as 1 star 0. And this is a finite state machine. So this A is the start state. And as you can see, I can, if I start off at state A and I have a sequence of 1s followed by a 0, if I'm at this state A and input 1, I can take this transition and end up in the state A, take another. So I'm just taking this loop over and over again. And at some point when I see a 0, it's going to take this transition and end up in B. We know that B is a final state, so it accepts this string. And you can see that you can accept any number of 1s and end up with at the final state B here. Notice that if I give the input 0, then starting from this start state A, I can just take this transition on 0 and end up with a B. So I start from A and I end up in B, and I can still accept it. So that's, as you can see, that 0 belongs to the language of 1 star 0, so it does accept it. This finite state automaton accepts the same language as this regular expression, 1 star 0. Okay, so what regular expression does this automaton accept? As before, find this, just clarify that A is the start state, C is the final accepting state. So if you look at this finite state machine, you can see that it has some kind of structure. So I want you to notice the sort of structural properties. The first thing to notice is there is this loop on A, which is equivalent to a regular expression 1 star, right? So it can accept, you can either take 0 of those loops or 1 or 2 or 3. So you can have any number of ones. Similarly, if you look at this part here, this looks like a 0 star. So why are there 3 states? So it starts off from an A, and then it goes to a B, and then goes to a C. So the path to a final state involves going through this state B, and the reason, as you can see here, is that it's looking for 2 zeros before it can reach a final state. As soon as it sees a 1, like either here or here, it goes back to the start state A and keeps accepting any number of ones that you want, as long as you end up with 2 zeros at the end. So from the structure of this finite state machine, you can see that it's supposed to end in 2 zeros, and then you can have any number of ones or zeros as long as you end 2 zeros at the end. So if I was to write down the regular expression for this finite state machine, it would be 1 or 0 star 0 0. Let's look at this recognition algorithm for a particular example. So take an input string 00100. We know that it ends in 2 zeros, so it's going to be a string that's accepted, right? So we want to end up on the final state C here because we know that it's a valid string. Okay, so we start off with the start state A, and the input, we haven't scanned anything yet from the input, so the input head is just over here before the first symbol. We can read a 0, right, and then go to state B. We can read another 0 and end up at state C, and we are at the final state, but there is more symbols left in the input string. So when it sees a 1, it's going to take this transition and end up back at state A. And then it's going to take the same 2 transitions it did before and end up in state C. And we can see that state C is the accepting state, so we can say, yes, this string is accepted. There's nothing left after this last, this element here. So we can say this string is accepted by this finite state machine. So that's an example of what the recognition algorithm does. It just looks at the next symbol and then does a transition to the next state, etc. Okay, so that's an example of a finite state machine that is very straightforward, because for every input I can essentially take only one step, right? So when I'm in state A, if I look at what are the choices I have, I know that the alphabet here is 0 or 1. So I have 2 choices. I can either make a transition on a 0 or a 1. So notice that both of those candidates are covered. If it's a 1, it stays at state A. If it's a 0, it goes to B. If you look at B, it also has 2 choices, a 0 or 1. And a C also has 2 choices, a 0 and a 1. So notice that for every state, so any state in this finite state machine, either for a 0 or for a 1, there is a transition to some other state. I mean, the state could be itself, like it could be a self loop, or it could be a transition to some other state. So it could be from one state to a different state. This algorithm that's used to either accept or reject a string is sometimes called a simulation algorithm. This particular finite state machine had an interesting property in that every time you see a symbol, so if you're at state A, and if you see a symbol either 0 or 1, you know exactly where to go. There's exactly one state you can go to. Similarly, if you're in B, if you have a 0 or a 1, you know exactly one state. So if it's a 0, you're going to go to a C. If it's a 1, you're going to go to an A. The same holds for the last state, which is C. If it's a 0, you're going to go to C again. And if it's a 1, you're going to go to A. So notice that for any input, because the input can only be zeros and ones. Here the alphabet, as you can see, is just zeros and ones. For every input symbol at any state, you know exactly one state that you have to go to. Like the transition function tells you exactly which state you're going to end up with. And then you go to that state and then look for the next symbol and so on. So now let's make our finite state machines a little bit more expressive. And let's introduce the notion of another kind of transition, which is on an empty string. So we call that an epsilon move. So it's a transition that's on epsilon, state A. On the empty string, I can go to state B. So if I am at some stage in the input, let's say I have an input x1, x2, x3, and I'm at state A, I can, without accepting any further input, like the input head stays at the same place. So that's what it means when you take a transition on an empty string, is that you don't move your input any further in the string, but you can take a transition to another state. Based on this notion, so a deterministic finite state automata can be defined using two rules. So rule number one is that there's only one transition per input per state. If I'm at state 1 and I take a transition on A, I shouldn't have sort of two edges on the same input symbol. So that's considered invalid in a deterministic finite state automata. And you can see why. If you're at state 1, I want to know exactly one state I need to go to on an input symbol. If I have a choice between two different, then I basically have to say, I don't know which one. It's either 2 or 3, and I should try both. So that's not deterministic. Hence, it's not allowed in a deterministic finite state automata. Rule number 2 is that you cannot have any transitions on the empty string. And that again is sort of clear, because if I can go on the empty string, I can end up in this sort of sequence of moves with the empty string and end up back where I am, and I haven't accepted anything in the input yet. So a deterministic finite state automata, we want to make some progress. Every input symbol should take us either closer to the final state, or we should reject this string. A non-deterministic finite state automata is more permissive. It lets you have transitions on the same input symbol to two different states. So it's allowed in a NFA, and it can have epsilon moves. And you can see that it can in fact have multiple transitions on the empty string going out of the same state. And this is allowed as well. So a DFA exactly has one path. It's always sort of single-mindedly trying to get towards a final state. And if at any point you have a input symbol and there is no transition on it, you know that you can just reject that string. In contrast, the NFA, on the same input symbol A might end up in sort of different parts of this state graph. And because of the introduction of the empty string, it can take that sort of transition into that path as well. In order to say whether this NFA accepts the input, it's going to accept an input if on any path, somewhere here there might be a final state, or somewhere here there might be a final state, and then somewhere here. So if any of these paths ends in a final state, then we have to say that it accepts the string. So it's non-deterministic in the sense that it explores this entire state graph, and if any path leads to a final state, then it should accept the input string. So let's take an example of how recognition works with a non-deterministic finite state automata. So when we are looking at an input string, so let's say we have an NFA that's shown here. We can see that it's an NFA because if I am at state A on an input 0, I can go to two different states, right? I can go to itself. A can go to A on input 0, and A can go to B on an input 0. So you can reach on an input 0 two different states, A and B. So let's say the input is really simple. It's just 1, 0, 0. And I start off with a state set. So we're going to generalize. Previously, we only had to track one state at a time, because in a deterministic machine, whenever you make a transition, you go to exactly one state. But now we can reach multiple states at the same time. So what we're going to do is use this notation, this set, and inside this set is all of the states which you can reach. So in this first case, there's only one state. So this set contains exactly one state, which is A. And then it takes a transition on 1, and you can see it's a transition back to the same set, which contains just A again. Now it becomes more interesting. On input 0, you can go to two states, either A or B. So we're going to represent that as a set, which represents that I could be either in state A or in state B. So it's either or. And if it could end up in all of the states in a finite state machine in some cases. And now we take another step of 0. So notice that what does this mean now is if I am in a state like this, what it's saying is there a transition on 0 from A? Is there a transition on 0 for B? Is there a transition on 0 for A? Yes, there is. It goes to A. Is there a transition on 0 that goes to a different state? That's also true, right? So A, remember, has 2 transitions out of A on 0. So one of them goes back to A, the other one goes to B. So from A, I can go on a 0 to A and B, and from B, I can take this transition and end up at C. If I was in either A or B and I see an input 0, where can I end up? Well, I can end up in either A or B or C. And that's our new set of states that we can end up in. And now we're at the end of the string here. One of these states in this set that we could be in is a final state, right? So C is a final state here. And so if any of these is a final state, we say yes, it is accepted. So 100 is accepted by this NFA. To see whether you're following along, I encourage you to do a couple of questions to track your understanding. So write down a regular expression for the NFA shown here. So this NFA, convert it into a regular expression. And the way to do it is by understanding the set of strings it recognizes and then write down a regular expression for that set of strings. And draw an NFA for this regular expression, which is 0 or 1 followed by 0 or 1 star. So what we want to do next is take a non-deterministic finite state automata and make it deterministic. There's some advantages to being deterministic. So when you're at a state, I know that I'm exactly going to one state. That's property of a DFA. And that makes recognition of strings really easy because all you have to do is either it gives you a transition to another state or you reject the string right away if you can't find a transition. And if you end up at a final state at the end, you accept. So a deterministic finite state machine is a lot easier to use at runtime. Sort of efficient as well to not have to keep track of a set of states. So the way that we're going to do this is by using the subset construction, and that converts a NFA into a DFA. So if I have this NFA over here, the idea is exactly the same as what we did for the recognition algorithm for an NFA. We're going to keep track of the set of states, but instead of doing it for a particular input string, we're going to do it for every state and for every set of states and for every input symbol. Here, we know that the input symbols are either 0 or 1 because here the alphabet contains just 2 symbols, and we're going to look at every symbol in the alphabet and ask the question, what are the set of states it can get into on that input symbol? So let's start with the start state. So the start state here is A, and on input 0, it's going to take either this transition or this one. So you can either end up in state A or state B. So this notation here that we're using is a set notation, and it says what subset of the original set of states in this NFA can you end up in on a particular input symbol. So if I'm starting from the start state, so this set just contains the start state and nothing else. And then on input symbol 0, I can end up in either state A or state B. So when you look at this set notation, you should think about reading it out in English as, oh, I'm reaching a set of states, so I can either be in state A or state B. What happens on input 1? Notice that I end up back at state A, so I'm back in a set containing only the state A. Now we know for this state, this set of states, which can, in this case, the set contains just one element A. On a input symbol 0, I end up in this set of states AB, and on 1, I end up sort of back to itself, essentially. So now let's look at this state, AB. So if I'm either at A or B, then if I take an input symbol 0, let's examine what can happen. So on A, if I have input symbol 0, we already know that A is ambiguous. on an input symbol 0, it can either end up taking this transition to itself or going to B. So it has two options. It can either end up in A or B. And if I'm at B, I would take this transition on 0 and end up at C. So now I'm in a set of states which is either A or B or C, right? So if I'm starting from either A or B, I can end up in either A or B or C. And now if I'm at A or B and I take 1, B doesn't have any transition out of B on 1. So essentially this is a dead end, but A does have a transition. So we end up with a set with only A in it. And notice that we have already covered that over here. But this is a new one we haven't seen before. So let's cover this guy. So we've already seen this. We've already seen this. Now we need to cover the set containing A, B, C. And now again, we ask the question, on a 0 or a 1, what can happen? I'm at this set of states, either A or B or C, and I see an input 0. Well, we've seen this kind of before, because on A or B or C, we know that A can end up either in A or B on input 0, B can end up in C, C can't go anywhere on 0, so that doesn't contribute anything. So I end up in this set of states, A, B, C, and notice that it's the same as this. On input 1, B and C are dead ends, right? On input 1, only A can go to A on input 1, so I end up with this. I've not uncovered any new subsets, like there is no subset for AC that comes up in this search. So not every subset of the original set of states would necessarily be in a deterministic finite state machine. Okay, so now what we've done is actually constructed a DFA, because each of these set of states I can consider to be a state in a deterministic machine. So notice that I have 3 states. This is the first state, the second state, and the third state. And the names for these states can be the set of original states that we had. So we first start with set containing A. On a 0, I end up with AB, and on a 1, it ends up with A itself. So it's got a loop back to itself on the input symbol 1. And now starting with AB, on a 0, it ends up with ABC. And on a 1, right, it ends up going back to the state A. And now from ABC, let's consider what happens if you get an input 1. It goes back to A, right? So we can see this matches this here. And if I have an input 0, it just goes back to itself. So now if I clean up these states and just reorder them a little bit to make it cleaner, I now have a DFA that's identical to the one that we had started off with before, right? The one that, remember, was equivalent to 0 or 1 star 0, 0. And it's deterministic, as we saw, because on every state, if you look at every state here, on any input symbol, it gives you exactly one state to go to. The key here is that when I have any one of these states in the set of states from the original NFA, if C was a final state, then this entire state becomes a final state. We always start with a state that is just consisting of the single start state. So we always know what the start state is, and we know all of the different final states. Because if you have the final state from any of the final states from the original NFA, then we call the state in this DFA as a final state. Another question for you to do by yourself is to write down the regular expression for this DFA shown. What we've seen in this video lecture is the notion of a finite state machine, and we saw these 2 flavors of finite state machines, a non-deterministic one called NFA and a deterministic one called DFA. And they recognize the same set of languages. So if R is a regular expression, then either an NFA or the DFA for this regular expression should accept exactly the same set of strings. DFAs are faster and easier to implement because they're deterministic. and it doesn't have to consider like all the different choices of states because it's deterministic. And DFAs usually have fewer states than NFAs. Not always, because sometimes you might have many more states in a DFA. So in the worst case, DFAs can be actually exponentially larger than an NFA. So when it comes to implementing a good regular expression matching, in order to match the regular expression, it has to do some conversion, which is what we'll look at next. But there is going to be a choice whether it converts it to NFA and then converts it to a DFA using the subset construction as we saw. Or maybe sometimes if the DFA gets exponentially larger, maybe it's better to use the NFA. So there's going to be some trade-offs, and that's why it's useful to learn about both NFAs and DFAs in order to implement the matching in regular expressions.